Hello, everyone, and welcome to my workshop. Today, we're going to be talking about building a better model with data augmentation. Specifically, we're going to be looking at images, but know that some of this can be translated to sounds or accelerometer data. That's what we're getting at. But images, I find, are a little easier to comprehend when you start talking about data augmentation. So you start with a basic image, we're going to move it around, maybe rotate it, zoom in, and create a whole new data set from those images. My name is Sean Hemel. I am a machine learning instructor and engineer. I have two courses. I'll share the links to those at the end of this, but feel free to check them out on Coursera if you want to learn more about both getting started with TinyML as well as computer vision using embedded machine learning. And that's what those two courses are about. They're on Coursera, and we use Edge Impulse throughout it just to give you a hands-on experience using all of that. We have live chat going on. I've got a couple of people checking that. So if you have any questions, please ask. And as we go through this, there will be a couple of points where we stop and we just kind of sit and wait for something to unzip or wait for a model to train. So that's a good time to answer questions, but feel free to queue them up in the chat. I'll also do my best to try to keep an eye on it, but I know I've got some people also helping me out with that. So what are we going to be covering today? If you have not done so already, please head to this link. If you are following along, if you just want to listen, great, I'll show it to you. Otherwise, please feel free to head here and work along with me. We're going to be going to this GitHub link, and this is EI Workshop -data -augmentation. It goes to one of my GitHub repos, and the README is actually a walkthrough, and just feel free to start working through that. I will not be offended if you work ahead of what I'm showing here. So feel free to do that and ask questions along the way. And there's a couple of spots where you actually get a chance to implement your own code or call some functions. So I challenge you a little bit throughout that, and I'll stop and show you where that is. But throughout this, let's see what we're going to be doing. First, I'm going to show you how to examine an original model, something that has been already trained. I've got it trained up on Edge Impulse. It's a convolutional neural network that spots electronic components. Resistor, diode, LED, capacitor, really basic things. And there's only about 50 samples per, which makes for kind of a poor model. It's an okay place to start just to get something going, but you'll see where it's not very accurate. We're going to get an idea of how that model is thinking. And we're going to do this using two techniques. One is called a saliency map, and the other is called a class activation map. And I've got some code to show you how you can take an image from there. We're going to create saliency and class activation maps, and you can start to get a sense of what's going on in this black box of a convolutional neural network. From there, we're going to examine a few different image augmentation techniques. These are very simple techniques: basic translation, rotation, zoom and crop, adding some noise. And then we're going to create a augmented data set using those techniques and then train up a new model, which will be the exact same model, but with hopefully better data. And you can see where the accuracy is different between those two. So let's start by heading here. And I believe we want to come back to that part. So I'm going to actually go to this. And if you paste this in, it should lead you to this GitHub repo page. So that's what's going on right here. Here is the README, and feel free to follow step by step. You're going to need an Edge Impulse account if you don't already have one. You will also need Google Gmail because we're going to be running some Colab scripts. If you happen to have Jupyter Notebook with TensorFlow and all that goodness installed locally, feel free to use that. But I find Colab just a great way to get up and running because it's all web-based anyway. The thing we're going to do is navigate to this old project that I have, and you should just be able to click on this link. It should come up, and you should be able to clone this project if you want to play with it. But really, we're just going to look at it. This is a public project that I created, and this is actually a project that's from the Coursera course. And it's one of the things that we do is I have students upload this data set, or they can upload their own if they would like. And let's look at some of the samples here. Here you can see a resistor, and feel free to go through some of these. Let's skip ahead. Oh, here's a diode. You can see that's a diode. I just took pictures of these. I think these come from an OpenMV. It's just I took a bunch of pictures on a white background so that I try to control the background. Obviously, that's one of those things that can affect how the model behaves. So for this simple example, I just kept a pure white background for everything. It makes it a little easier so you can get an idea of what's going on. Accounting for different backgrounds, it starts to get a little interesting. So simple set, 5 different labels. And you notice for the training set, there's only about 40 samples per. And if you think about it, this is a 96 by 96 color image. When we go to extract features, what we're doing, let's go to the create impulse first. The images get resized to 28 by 28. They are also converted to grayscale. So it's no longer color, but still 28 by 28 grayscale. So that ends up being what, like 780 something dimensions. That's the input to this convolutional neural network. Convolutional neural network. That is a lot of features, and 40 samples per class is really not a lot of samples to train this. When we train it, where is my classifier? There it is. It actually does decently well. There's enough difference in variability among the classes that the model can go, okay, where this pixel is kind of dark in comparison to the background, that's probably a diode, or that's probably a capacitor. And those kind of relationships are basic enough to figure out, but likely there's some overfitting going on here. 90% is an okay place to start for something like this. But you can see I run into a lot of false negatives and false positives, especially between something like diode and resistor for this particular model and this particular training set. And if we head to not live classification, model testing, you can run inference on all of these test set samples. And let's pick one here. Let's go to this resistor, and it was falsely classified as a capacitor. So if I click on this little drop-down menu, say show classification, and wait just a moment, and you can see this resistor in particular is kind of up towards the northern side of that frame, which makes me think that, okay, possibly the model is looking up there for dark-colored pixels, and it thinks that's a capacitor because the capacitors are large and they take up, a big circular section of the frame. So, okay, not great. It doesn't think that resistors that have been translated somewhere in the frame are resistors, and that's kind of a problem. In fact, it really thinks it was a capacitor, gave it 100%. And one of the things we can do is we can kind of look to figure out where the model is looking. And that's where we get into saliency and class activation. So I'm going to head back here to talk about what's going on in saliency maps and class activation. Class activation maps. Here is the convolutional neural network we just looked at. Fairly basic, 2 convolution layers. There's some pooling layers. It gets flattened to a vector. There's my dense layer out to a softmax to give me my probabilities. And to get saliency map to work, the first thing we have to do is we have to get rid of that softmax, because saliency actually uses the raw outputs of these individual nodes from the dense layer to do its computations to figure out which pixels were most important in the decision-making process. And we get something like this. We can convert it to a heat map where dark blue means these individual pixels were not very important in the decision-making, whereas you get up towards yellows, oranges, reds, that means those individual pixels were very important to make the decision that this resistor was classified as a resistor, or in our poor case, our bad case, it was misclassified as a capacitor. So that's a saliency map. A saliency map is which pixels are the most important in the decision-making process. That's kind of useful. As you can see, it's a little speckled here. It kind of shows you what's going on. Something else that's very useful is something that's known as a class activation map, and that answers which features, which is different than which pixels, which are your inputs, were the most important during the decision-making process. And I drew the lines coming out from first the input image, because that answers which pixels, and you can see the saliency map is 28 by 28. It should be the same dimensions as your input image, whereas a class activation map is in this case 14 by 14, and that's after a number of convolution steps and or pooling steps where your feature map has been reduced in size. And so those features, which you can think of them as pixels in this case because it happens to be a 2-dimensional array, that determines or that tells us the class activation map tells us which of those features were very important. GradCam in this case refers to gradient weighted class activation map. It's just a very specific algorithm used to generate this heat map. As you can see here, this kind of lines up with the pixels over here. I am honestly not super sure why this dark red pixel says it's super important in this upper right quadrant of the image here. But the idea that it's looking in this center region is pretty important. And in this case, this is not the same resistor I showed you earlier. This one was correctly identified as a resistor. So this says when it correctly identifies resistors, it's kind of looking in the center and looking for this sort of oblong shape, because these pixels are super important, or excuse me, these features are super important when in that decision-making process when these features get sent down to this dense neural network layer right here. So this is the resistor that I just showed you that we broke apart, and we can overlay the heat maps from the saliency maps as well as the class activation map on top of the original image, and you start to really get a sense of what's going on. What I find interesting is that even though this says the center pixels here were important, or the center features were important, it doesn't quite line up with the center pixels. So I wish I knew the exact answer as to why there's a big difference between saliency and class activation maps. That is something I still need to look at, but the combination of the two start to give you an idea of looking into the black box that is convolutional neural networks. Here's an LED. This is the saliency map. This was correctly predicted as an LED. And what's interesting here is, okay, the neural network was looking at the center area, kind of this oblong shape, but for the LED, it's looking where the LED is not, in this upper region, and the edges along this bottom region. It's also looking for kind of this top corner here and the rounded side of that LED, which I find super interesting. That a lot of times what you'll see is that during computer vision, these algorithms you create, they're not looking at the objects. They're looking at things that may not be the object or the subject of what you're trying to classify. And that's super important if you say, I'm trying to determine dogs or not dogs in an empty field to see if my dog park's being used. And you take pictures of dogs on cloudy days and not dogs on sunny days, and you go to deploy it and you're like, well, it thinks anytime there's a cloudy day, there's dogs. What's going on? Well, it turns out you didn't train a dog classifier. You trained a cloudy day predictor. That's what you did. So these techniques help you get insights into what's going on. Is my neural network looking at the thing I think it's looking at? And in this case, well, maybe not. This LED, it's being identified through other means than the shape of the LED. And that's kind of interesting. Here is an LED that was predicted as a resistor. As you can see, the leads are cropped off a little bit when I took this picture. And the saliency map shows me that it's looking at the pixels kind of around it, not inside of it, inside of the LED body. And what's interesting is you come down and you look at the GradCam image, and sure enough, it shows this curve here, but it's kind of it's lining up a little bit with how it predicted a resistor in the center area. And it's not looking at the top features or the bottom features that's part of the background to determine that's an LED. That to me says something's off, that what I've created is a model that's looking at the background to make some of these decisions, and that's not really what I want. So let's do this for real. Let's head to the Edge Impulse project. I've got this 19.png. We know that this was misclassified as a capacitor. And what I'm going to do is I'm going to take this image, I'm going to right click and say save image as, and I'm going to get rid of my previous one because I tried this last night to make sure everything worked, because demo day. Oh, it already exists. Okay, well, let's save that anyway. So that's going to download. That's an actual image. And we looked at the old model. So we're back to the README in the GitHub page. We're going to look at the saliency map and class activation map. We downloaded them. We downloaded the image. The next thing we need to do is download the actual model. So back in our Edge Impulse project, go to Dashboard. And if you scroll down, you'll see download block output. And this is where you can get your .tf-lite files, your actual TensorFlow saved model. And that's what we want, because we want to get that model and we can remove that final softmax layer. So I'm going to click download and get my model file. And then I'm going to open this Colab notebook. So there's a link right here. I'm going to open it in a new tab. You might get asked to sign into Gmail if you're not already signed in. And feel free to read this. I'm going to press Shift Enter to run these cells. I'm going to import all of the libraries. You might get a pop-up that says not authored by Google. That's fine, run anyway. And we can change some of these settings. So the first thing we need to do is upload our saved model, the thing we just downloaded right here. So if you've never played with Colab before, it's basically a full Linux instance. It's really limited in what you can do. It's essentially set up just to run Jupyter notebooks. But if you look in the files browser, you can go up and sure enough, there's your root directory. We're going to be working in the content directory. So I'm going to right click and say upload in there. And here is the model file that I just downloaded. So I'm going to open that. It says it will be deleted from this runtime instance, which is fine. Something I've run into with Colab is it doesn't like parentheses sometimes. Maybe somebody can explain what's going on there. But I'm going to rename this file and get rid of these parentheses because that does not matter. The next thing I need to do is upload this PNG image. So content upload. I just downloaded this PNG image, upload it. And this will probably work, but I'm going to rename it into something similar. I don't know why I can't drag that across. There we go. So now I've got 19.png and the name of this file. If you need to rename this because it's coming from a different project, you can right click on the file and say copy path. And then I'm going to get rid of this long string here and I'm going to paste this in and it should be the same, but that's my model file. Make sure that your labels line up with your, I got rid of that. So let's open up this classification. Oh, here it is. I can't see because I've got Zoom stuff going on. Need to click that tab. So down here, make sure that your labels line up with these, and you want the ground truth label for this, which is resistor. So these should be in alphabetical order: background, capacitor, diode, LED, and resistor. The ground truth label is resistor, and make sure that your 2828 lines up with what the project expects for your features. It should get scaled to that 28 by 28. So we're going to Shift Enter to run that. And we're going to basically just Shift Enter to run through all of these, where it's going to get the index of the labels. So resistor becomes 0, 1, 2, 3, 4. It's going to unzip that model file so you can refresh the files. You can see save model. There's your .pb, your TensorFlow model. It's going to load that into memory. The next thing it's going to do is extract the features, which means convert our image to that 28 by 28 grayscale, the same thing we're doing in Edge Impulse. The Keras model expects a 4D array because it expects number of samples, which there's only one, your width or your height, width, channel, and there's only one color channel, so that's fine. Then we're going to do a forward pass, and you should see capacitor being nearly 100% as the output of your softmax layer. For either algorithm, we actually do need to remove that softmax layer, and that's what we're doing right here. Then we're going to create the saliency map. I'm not going to go through line by line what's going in this code. We're just going to use it as a tool right now. And we're going to call that function to generate the saliency map. We're going to draw it. So here's the basic output, and then we're going to overlay it, just like I showed you on that slide. And sure enough, it's kind of looking at these top edges to create the decision about the fact that this is a capacitor rather than a resistor. And I won't do it right now, but feel free to go grab a capacitor image and run through the same thing to see if it's kind of looking in that same region. Then we're going to do GradCam, and here's all of your code to do GradCam. We need to tell GradCam where to find that last convolutional layer, and that's what we're getting the output of to create that class activation map. We're going to generate the heat map for the GradCam image. We're going to draw it, and there we go. That looks like the GradCam images we saw earlier, and we're going to overlay it. So that involves scaling that image up so that the 14 by 14 overlays nicely on that 28 by 28. And sure enough, it's looking in this region of those features, overlaying with that with the image to try to give you an idea of where it's looking, general concept. So next up, we go back to this README. We've done all of that. We've got our images. Now it's time to create a data set, an augmented data set. To do that, we want to open the Transforms demo collab. So that's another collab instance we're going to be opening. We're going to Shift Enter to run this. I will probably get yelled at by Google. Yes, that's fine. Run anyway. And this is not the augmented data set yet. These are some examples of transforms that you can use to create your augmented data set, specifically looking at images. And what I'm going to do here is I'm going to pull an image that I've just got saved on the internet. It's the first image, the first resistor image in that data set we used to train that original model. We're going to load that image as a NumPy array. We're going to grab the width and the height so that I'm not hard coding that. And we're going to take a look at that image. Sure enough, it's a resistor. Hooray! The very first transform we can do is a very simple flip. Left, right, up, down, and left, right, up, down. So we're going to create 3 new images from this original image on the left. And this has a number of benefits. For example, maybe your model is looking at the dark pixels that create the shadow underneath the resistor, and I didn't create enough original images that are on top of, on this side, on the other side, so that the shadow shows up in different areas of the frame. So your model may be going, oh, I always see a shadow here, and that's a resistor, and that's not what you want. So by flipping it, you can actually put the shadow on the upper side, the other side. So you're telling the model to look for something else, like, oh, this is still a resistor. You should be looking at other things. Or maybe it's the glint, this little shiny piece right here. What if that's always on the upper left? Well, by flipping it left and right, that's now on the right, and up and down, left, right, you can start to see that we're now going to kick the model to saying, oh, that's not always necessarily a resistor. If the glint is over here, you need to look at other features in this input data to make this happen. So this, we're just expanding the data set from one original image. Another thing we can do is rotate it. Here I've rotated it, what do I have? 45 degrees, 90 degrees, 135. All of the images in the original data set that I took have these, oh, somebody's going to correct me, these axial or radial. I never remember. I think these are axial leads coming out to your sides. They are always left and right to your sides. I did not take any like this. I did not take any like this. And that can be a problem if your camera, or say this is a conveyor belt and you've got these resistors coming along, and instead of being this way, the resistor is now this way. What happens? Because it was never trained on that type of image. So augmenting the data to say, you know what, if the leads are like this, that's a resistor. If the leads are like this, that's still a resistor. So you're saying, okay, you need to pick up on general shapes in the component body rather than the direction of the leads. And this can help fight things like on, production, where you don't know what type of orientation that your original object is going to come in at when you're performing inference. Something else that's interesting is, how do you deal with the sides of the image where you don't have pixels? So I can change this to constant, and you can see that it just fills it with white pixels with constant. I think there's a way to get it with black pixels if you're working with, say, a dark background, but edge actually takes, when I change this parameter to edge, it takes the pixels that were on the edges and it just copies them out. It just extrapolates them, which works wonderfully for things like my components here, because it's actually extrapolating out these lead pixels, which weren't there before, and it happens to still look like leads, which is how I would expect this. But if this is a face, you'd get like half a face and then like this stretched pixel image, think like Windows crashing and you're dragging a box along kind of thing. That kind of look is what you end up with if it doesn't lend itself nicely to kind of copying these edge pixels out. But edge pixels work great for this case, so I'm going to keep these. You can also do things, you don't have to do 45s, you can do 15 degrees, and you kind of get an idea of what's going on here. So the next thing we have is scaling and randomly cropping. And I'm going fast through this code, but it's all up on that GitHub repo. So feel free to stop and look at that code if you'd like to get a sense of what's going on. But it should be, I hope you're at least getting a sense of how we're creating these augmentations just by visually inspecting this. And I hope you can also see that, oh, this might be, some of these things might be useful for other types of data, maybe accelerometer data, like a time series, or sound data. And you can think, oh, maybe I've got my spectrogram, right, for sound, and I can shift it left or right, and that gives me more positions where my keyword might happen for something like keyword spotting. But if I shift it up and down, now I'm changing the frequency, and maybe that's something you want or don't want. So think about it carefully when you're working with other types of data. So your translations might work well for sound, but your rotations, if you take a spectrogram and do this with it, that may not work very well. But images are a great way to start working with data augmentations, because it's very easy for us to see, oh, what is a translation? Oh, it's just moving it. What is a rotation? It's rotating it. So the other thing you can do is these zooms and crops, these random zooms and crops. So I'll run this so you can see it. And this is just, I take the image, I blow it up, and then I just take a random area and crop it out. So I still end up with this, I guess it would be 28 by 28 when I extract features, but since I'm working with the original 96 by 96, these become 96 by 96 color images. But it looks like I've just moved the camera in a little bit towards it. This is very helpful if you can't control the exact height of the camera where you're taking these pictures during inference. Say I created a training set and I always held the camera, I don't know, a foot or 50 centimeters or whatever it is above where I took these pictures. And I go to deploy this and I can't guarantee those 50 centimeters. So what happens then? If I move the camera in, it starts to look like these images where it's zoomed and cropped and we don't know. So creating these augmented data sets like this that include these zooms and crops is a good way to do this. And I think I do like 1.2 or 1.5. Here we go, 1.3 zoom. So feel free to experiment with 1.5, 1.2, and you could create different scale factors. Then we have, so these weren't translations. These were flips. Now I'm doing translations. I misspoke earlier on the translations. Here are your translations. That's where you take the object and you maybe slide it this way, maybe slide it up, maybe slide it over here. And it's just kind of the idea is you're taking the camera and you're just moving it around in that plane to take the different images. This might work very well for something like a spectrogram. Flipping it is probably something you don't want to do, because then it's like, say you're saying the word backwards. That's no good. And I've got my translations, and these are just randomized. That's all I'm doing here. If you want specific ones, you can put those in, but these are done randomly. And not going over a certain, was it like up to a fourth of the image in width and height. Finally, we get to noise. And there are a few types of noise that you will come across in images. The first is your random white Gaussian noise that happens in a lot of signal transmission. It happens a lot in images, especially as you crank that ISO gain up. You start collecting a lot of noise on your sensor, and that shows up in your images like this. So if you're working in low light situations, or you just want to have noise in there because you want to tell the model it may have a noisy input images based on whatever your sensor is, that's not a bad way to do this. Is just to add some Gaussian noise. Salt and pepper noise, I don't see very much. It has something to do with the way the individual pixel sensors pick up something weird. I have not run across this for many digital images, but apparently it's a thing. So if somebody knows, feel free to leave a comment about how salt and pepper noise comes about. I read about it once, and I honestly do not quite remember what creates salt and pepper noise. So I hope this gives you some ideas on very basic translations, or excuse me, basic augmentation techniques you can do: translation, rotation, adding noise, and so forth. There are basically infinite number of ways to augment image data that you can think of. These are just really basic ones you can start with, and a good way to create an augmented data set. You can play with color channels. You can play with skewing the image. You can play with zooming or warping the edges, or stretching. There's lots of things you can do to augment it, and it kind of depends on your application. And think about how you might encounter these things when you go to deploy your model and start performing inference on new data, and what you might expect to see. And augmentation is a good way to start creating some of that data from a very limited data set to start. All right. And Anouk says hi. Hi, Anouk. Now that you have an idea of what this augmentation looks like, the next thing we're going to do is create the actual data set. We've got some ideas, we've got some functions to start with. Let's open up the augmentation creation. So I'm going to go to, so I've got 1, 2, 3. I'm going to organize these. So here's the new one. Workshop 3, data augmentation. This is where we're actually creating the data set. The first thing it's going to do is, of course, yell at me because Google did not author it, which is fine. Then we want to take a look at some of these settings. It's going to download that original electronic components data set, which is, I think it's like 50 images per class. It's just going to download those. I've got those hosted on GitHub, and it's going to download them in a folder. And I need to set my output path. So you should not need to change any of these. I run the next cell. It's going to download those. I believe it unzips them. Refresh this. Yep, data set. So here it is. Yeah, feel free to look through here. I've got capacitors. So if I double click on that, I can see it's a capacitor. I can double click on my LED. Sure enough, that's an LED. Okay, this is the whole data set. And I've got about 0 through 49, so 50 per. So not a big data set. This is the original one we trained that model with. We have creating an output directory. So we're going to run that cell. You can refresh the files browser here. Here's the output directory. That's where the augmented data set is going to be stored in this, from this script that we're working on here. Then I'm going to define some transform functions, and I've done my best to quickly document them here for you because it will be your job, and I will walk through this as well, of calling these functions. So the first thing we're going to do is create a set of flipped images. So we provide it a flipped NumPy array, which represents the image, and it's going to create a list. So here's my blank list, and it's going to create flip left, right, flip up, down after flipping it left and right. It's going to just create this list of 3 new arrays and then return that list. So that's my first function. Then I'm going to create rotations. And for here, I believe this is a list. So if you look rotations, this is my parameters. It's a list of floats, and you just list out what kind of rotations you want and the degrees, which I believe is between 0 and 360. And oh, here's an example of me calling this rotation function, or create rotated. So here's the list: 45, 90, 135. And here I'm using skImage, their transform function, to just create that rotation. Then I've got my random zooms. To do this, I want my image, my scale factor, 1.2, 1.3, and then just number of crops. And it just randomly takes sections of that zoomed image. And then we have create random translations. That's where we move the subjects in different spots, number of translations, and it's just going to randomly move those. That's all that's going on in here. So we have the random up to 1/4 the image width and height. It's going to create a list just like we saw before and return that. I am leaving noise blank. So anybody working ahead, that is a challenge for you to implement noise. And if you want a hint, if you go back to that number 2 collab, how to create random noise is quite literally right here. So all you have to do is wrap that in a function. I'm giving away too much. So I'm going to skip that one for now. That is exercise for student if you want a challenge while you're working through this. Then we need to call these functions. So we've got create transforms. This is just a function that does all the transforms. So a file path comes in. It says, oh, where is this particular image? So we've got my data set. Maybe it'll be data set background 0.png. That comes in here. It opens it using PIL, which used to stand for Pillow, or the Python imaging library. I guess that's the acronym now. It's going to create an NumPy array out of it. And it's going to create a list, and it's going to start appending the original image and then each transform to that list. So at the end, I've got this big list of all of the original image at the front, and then all these transformed versions of the image when it's this particular function is done calling. So here's the first example where we create flipped. So let's add, so we've got zooms, rotated, flip images. So we did that one. Let's get our rotated. And in fact, here's just, I'm just going to grab this example. And we don't just want to call this function. We want to call it and append it to this TF's list that I have going on here. So we've got append, create rotated, 1, 2. And then the next thing we want to do, so we did rotated, we got flipped, we want the random zooms. So let's get my create random zooms. And you know what? We're just going to use this one, 1.3 and 2. And I'm going to do IMG, TFs for my transforms, append, create random zooms. What is next? So here's my random zooms. Here's my random translations. Nope, that's random zooms. I found a bug. I forgot to update these examples. So we're going to call it from here. It does work. It's not technically a bug. It's just a fail in documentation. So we're going to pass it the IMG. And the other thing I forgot to do is instead of IMG, it should be my IMG array. Come on. There we go. Because that's my NumPy array that represents the image. We've got number of translations. So how many translations do we do? 3. 3 sounds great. So we're going to run this cell. That'll define this create transforms. And then we are going to actually run the script where it loads each image, calls this function with each image that creates the transforms, and then creates all of it generates the images from each of those transforms. And this is going to take, I don't know, a minute or so. So this is a good time to ask any questions if you have them. And moderators can also step in if they have questions as we're going through this. So some of the limitations for this include being mindful of what you expect to see for the translations. And it doesn't do things like occlusion, where you think about, oh, I've got a resistor and then I've got a capacitor on top of it. Well, is it going to see it as a resistor or a capacitor? I don't know, because part of it has been hidden. Possibly some ways to create automated data augmentation for occlusion. Fail in documentation. Yes, thanks, Jen. It was definitely a fail in documentation. I'll try to make sure to update the GitHub repo after this. And then once this runs, we should have our output. Feel free to go in here. Oh, the background is just background. This is going to be a collection, a terrible collection of white images, because that was what my background was. It's just a piece of paper. So it's just a lot of those. And if you translate pure white paper, it's just going to be more pure white paper. So let's look at something more interesting, like a capacitor here. 0_0. So 0 is the original image, and then _0 is a copy of that original image. So this is what that image looked like. And then the _1 is our first transform. So we've got the flipped, more flipped, flipped, and translate, either zoom and crop or translated, and it just goes through like that. So then you have, here's, I don't know, 14 _0. That's the original image, and then just the list of augmented images that go along with that. So this is our augmented data set, and the final cell zips it for me, just calling a background Linux command. And we have our augmented data set. So let's download it. It's taking a moment to download. So what I was saying earlier about something like occlusion, you could create ways to automate that. So let's say you take like a PNG and you have a transparent background, and you could take the PNG of the capacitor and you could overlay it on random spots of your resistor to create like some type of occlusion where parts of your image are hidden, or maybe you randomly take out chunks of it. And what I learned not yesterday, but the day before doing a roundtable, if you put a dropout layer at certain spots in your network, you can artificially create these types of random occlusions. So if you do random dropout at your top layer by your inputs, it's the same as saying, oh, I'm just going to remove random pixels. But if you do it later on, you're saying I'm removing random features that might be there. And so this might be entire chunks that might look like they're missing. So dropout layers are something interesting to play with when you're working with convolutional neural networks. They can help prevent overfitting, and you include them only in training, but you don't include them during inference. And all they do is they just say, hey, oh, this value that gets passed from this node to this node, from one layer to the next, randomly just don't include it. It's just not there. And that can help fight a lot of overfitting, because the model's no longer relying on that one piece. It has to look at connections across everything in order to make its decisions. All right, so I've downloaded my augmented data set here. And now, if you go into here, back to our GitHub repo, we say retrain the model with the new data. So let's go back to Edge Impulse. When that fires up, I'm going to log in. I am going to create a new project. Actually, I'm going to call it this. Just change the number. No, don't open it. Create new. There we go. There, new project, because I've tried this a few times to make sure it works. Apparently, I didn't check all my documentation, though. That's all right. So I'm going to go to data acquisition. Oop, and before I do that, I actually need to unzip my augmented data, extract all. You can see everything I've downloaded and did not clean before this. Augmented data set. And this is going to take a moment to unzip here. So while we're waiting for that, feel free to ask any more questions. Yes, questions. When the augmentation leaves some pixels empty, such as when you apply rotation, what is the best approach to filling those pixels without creating unrealistic artifacts in general? That's a tough one. If you saw earlier, so let's go back to these transforms. And so you were asking specifically about, say, rotations. So we've got these rotations here, right? And so you can fill it in with something. And it's hard to figure out what's going to be beyond those pixels, because obviously that's data that just wasn't there. So if I enter constant here for this SKA transform rotate function, I fill out constant for this mode parameter, it fills it with white. I believe there's a way to say fill it with black. So if you're working with light backgrounds, that might be good. If you're working with dark backgrounds, filling it with black might be good. And that's kind of a best guess. Sometimes you can do, there's a technical word for this that I am forgetting at this moment. It's called edge here. It's not quite extrapolation, but all you're doing is when I say edge here, it's taking the pixels that are at the edge and it's copying them out to fill in those blank spots. That works decently well for certain kinds of images. So your question is, what's the best approach? It depends on your application. In my case, when I did edge and I copied those pixels out to fill in those blank spots, that worked super well. That is great here. I can't guarantee if you've got patterns or other things at the edges, those are going to copy out and look super weird. Like think about somebody's face. If I crop a face here, you're not going to fill out with the rest of my face. You're going to fill out with just whatever pixels were right at this edge, and it's going to look like I just got stretched. That may work if you're just trying to get the model to pick up certain features, and it's okay if I copy these out. But if you copy out too much, it doesn't look like what you're intending. So I recommend carefully thinking about how to fill in those blank spots, especially if the model's not supposed to be looking at the center, but potentially edge cases. I hope that helps answer that question. All right, Jen has a question. In terms of doing rotations, translations to get new data from existing data, could that increase the model bias? That is a very good question. Yes, if you have bias in your original data set, and if you just create augmentations, you could maintain that bias. That's a very good point, of a big risk and possibly a lot of limitations. I'm trying to think of a good example of I always think of like racial bias, of like, oh, you trained it on light-skinned individuals and the model doesn't pick up anybody else that's not a light-skinned individual. Like that's no good. So if you augment those data sets, well, obviously it's not going to pick up data that wasn't there. You're just moving the face around. So constantly make sure that you're not introducing or furthering any bias that was already in your data set. And yeah, this is not a replacement for good data, collecting original good data. Something else, another form of bias happens if you have an unbalanced data set. So if I didn't augment and create more background images, even though they're just kind of copies of the same, I might end up with very few background images and a lot of other images. So now my background is a very small part of that data set. So the model might start going, oh, I'm just not even going to try to predict the background anymore because I'm more accurate that way. And so maintaining that balance is also really good. So you have to remember that. I hope that answers the question. And let's see, I think it finished unzipping. Yep, Windows is not yelling at me. I think that's good. Let's collect some data. So I'm going to upload the data manually. And I'm going to go to my augmented data set, and this is going to take a moment here. So output, background, this is what I was talking about. Everything's just a white background. So I'm going to open that. I'm going to leave it on automatically split between training and testing. I'm going to enter a label, background, and begin my upload. Let that upload. I hope my internet speeds. Oh, yeah, we're way good. Sweet. Yeah, thanks. I know there's more instances of bias that you can probably imagine in machine learning, but I'm glad that that helped. Yeah, I would not use data augmentation as a way to fix bias. It will just make biases worse. That's the best way I can put it. And now that background is done, we are going to go to capacitor. We're going to get the capacitor in here. Let's do that. Oh, internet's pretty fast here. I'm really happy with this. Yeah, so if anybody's seen any of my other videos before, I am not in my normal workspace. I am actually in an Airbnb in California right now in Mountain View. Awesome. Thank you, Jay. And by the way, if you haven't, go check out some of Jay's work. He does some really slick stuff with robots. Companion bots specifically. Let's do diode. Let's do diode. Begin upload. Go, 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 go. There we go. Now that diode's done. Sorry, this takes just a moment here. LED, almost done. Let's open up LED, change my label, begin upload. We do the little dance while we're waiting for it to upload, like that. And last one should be resistor. So begin upload. And as soon as that's done, we can go extract features from these, which is just going to be scaling and converting to grayscale. All right. So I recommend clicking on data acquisition again. Always good to check. Sure enough, we've got 350-ish items per class, which is a lot better than the original 50 we were looking at. And I didn't do as many. The first time I did this, I had like 3,000, but this hopefully makes the this session go a little bit faster here. So let's go create our impulse. And like I mentioned earlier, you want to make sure that's balanced. You want to make sure that that wheel there is fairly balanced among your classes. Let's change this to 28 to 28 by 28 to line it up and make it comparable to our previous one. We'll add a image processing block. We'll add a, I don't want transfer learning. I want classification keras. Cool. Let's save my impulse here and go to image. I want grayscale because I don't care about colors. Somebody was asking earlier about, can you make something that identifies the resistor value based on the bands here? And that sounds like a fantastic project. And maybe one of these days I'll work on it. So first you identify where the resistor is, find where the bands are, then line up the colors. There are probably several ways to do this, but it sounds like a fun machine learning project. Is like hold up a resistor to a camera. It goes, ah, that's a 100 ohm that you're holding there. Let's save my parameters. I'm going to generate features. GroupGit says hi. Hello. Thank you all for joining today and working through this. Generating the features. And as soon as this is done, we can actually go train our model and then compare it. And the other fun thing is we get the visualizer over here, which is one of my favorite features of Edge Impulse. Being able to compress, what is it, like 780 something dimensions down to 3 is super impressive. Here we go. So hopefully a little more separation among my classes here. It's probably, it might still struggle with, what is this? My resistors and diodes, like we saw earlier. That's a tough one. All right, let's go to my classifier and do the training. So I recommend bumping this up to, I don't know, 100. 100 training cycles. I'm going to do 50 for the sake of time. This is the default classifier, the default neural network that we get. It's the same as what we had in here. So I'm going to go to my classifier so that you can see it is the same exact classifier. And I'm going to start training. While that is going, I will answer more questions. Here we go. By the way, can you use a flood fill op, IM fill, to remove artifacts, such as empty pixels whole? I honestly don't know much about the flood fill op. Imfill, what library is that a part of? Because that sounds super interesting. I will have to look into that one. Yeah, if you have, do you know how it's filling those holes? What is it doing? And I know there's a delay between what I'm doing right now and on YouTube. So the last slide I want to show you, no, let's do Shift F5, is kind of this idea. What I showed you originally, I showed you in the second collab, we created 13 images out of just one. So the one, we flip it a number of ways, we rotate it a number of ways, and you can always increase these. We translate it, we crop it, we add noise, and one image, the first image plus 12 translations, or excuse me, 12 transforms, that's 13 new images. So 250 original images, we can create 3,000 images. And I've got about half of that right now for the sake of time. But you can see how we can just grow our data set just from some basic transforms here. And this is not even including stacking these transforms. So I could flip something and translate it and rotate it and then add noise. And you can see how I could exponentially create more data out of this original data set. And it may or may not be necessary to do. So once again, you want to keep training in something reasonable, because at some point you're going to get diminishing returns. But I find even these basic operations work pretty well. Hopefully these 1800 that I'm showing you, you'll get an idea. OpenCV, go back to the original question. OpenCV has that. Okay, I have not played with that IM fill operation. That sounds like a really cool one. So I'll have to look into that. But yeah, going back to this, we've got 3,000 images. You can get 10, 100,000 just from this original training set. But because of those diminishing returns, it may not be necessarily a good thing. For example, I may be more concerned about rotations because I only took images where the leads stick out left and right. What I want to do is handle more instances where it's like just shifted 15 degrees or maybe 20 degrees. So I may do more rotations and less of the translations, if that starts to make sense about what I'm trying to do here, because I only took these types of images, but this fills in a gap that I really don't have. Whereas adding noise may or may not be useful, or flipping it may or may not be useful. So play with it, see what works well for your particular applications. And training is complete. And even with only 1,800, you can see I got 97% accuracy. I still get some false positives, false negatives. The LED and capacitor kind of get confused. Resistor and capacitor, interesting. Resistor and diode does, but resistor and capacitor seems to have this 4% mismatch, which is interesting. So I always recommend looking at your confusion matrix rather than just pure accuracy. You could end up with a naive classifier if you've got class imbalance and your accuracy score is a kind of a bunk metric to look at sometimes. It's a good number that we can all conceptualize what's going on, but I always recommend looking at your confusion matrix to see if something's getting misclassified or if you have something like a naive classifier. This is way better than what we had up here. You can see that we don't have these obnoxious 30% mismatches between diode and resistor. And hopefully when you go to deploy it, and I did find this to be the case, I deployed it to an OpenMV and you could kind of move it around and see what's going on. And it does pick up the component a lot better than having to hold the camera at a very specific height or a very specific distance away from my component at a very specific center the component with the leads at a certain angle, and then it classifies it as resistor. This works a lot better. This creates a much more robust model for what I was trying to do. And we can go to model testing. Feel free to classify all. And I'm running out of time here, so I won't be able to go in, but feel free to do that saliency and GradCam collab again, but using the images that were generated, or excuse me, using the model that we have trained now with this augmented data set, you can start to see where it's still failing. So you can see it's much better. 92% is not as good as what we were seeing. So there is some overfitting, it looks like. So I was seeing 97% and I dropped some. So it looks like there's some overfitting, which might mean going back and generating more data. It might be tweaking some of your hyperparameters. What I found is when I had 3,000 images, this actually got up to like 96%. When I tried this originally. So there was even less overfitting. So as I add more augmented data, I could create a more robust model, and it worked better for some of these test cases. But we can go through and find diode misclassified as resistor, show classification. Feel free to take these, run them through Saliency and GradCam again to start seeing, oh, where's the model making decisions at this point? So it looks like it's struggling with vertical leads, which is super interesting. So maybe I need to generate more augmented data like this in order to train the model to identify this as a resistor. So hopefully this starts to show you how you can iterate on your model designs using something like data augmentation in order to create more robust models. And as we mentioned earlier, as Jen brought up, this may not create, this may not solve bias problems, but it can solve a lot of other problems, especially when you're dealing with like lighting conditions or camera distances and whatnot. So what's the GPU runtime you're using for training? What's the GPU runtime? I'm not super sure for training. Let's see. Let's see if I can go back to that. This is my original. This is the augmented one. Oh no, I'll hit the train button again and we might have time to look at it before we end here, because I did not see the train time up here. But it obviously goes up because I have what was 10, not quite 10 times the number of training samples. So I expect it to go up. It does take longer, which is why I use this time to go look at a slide. But yeah, you can see each epoch does take longer because it has to run through all the training, which I've got, I'm going to say 1800, but it's not quite that. Hope that helps. So any final questions here while this is going through this last training? I don't know if I'll get it in time, but we will see. I hope that answers the question. I wish I knew the exact runtime, but expect it to take more as you have more samples. And obviously, if you can parallelize some of these operations, if you're doing something like batch gradient descent, then you can probably do a bunch of forward passes in parallel and then update your parameters after. So that might help. Okay, cool. Yeah. Sorry. I wish I knew the exact answer. Like how much time does it add to training when you have this much more data? And I'm like, I wish I knew. It's more obviously, but how much more? Not sure. Awesome. Any final questions? If not, feel free to reach out to me on Twitter. You can also file an issue on that GitHub repo. Come on here, 36, 37. You can do it. It's going to also probably have to profile. Is it possible to load a pre-trained model? If you're talking about something like transfer learning, yes, I know Edge Impulse does support transfer learning, and they were doing mobile. Wait, no. Was it MobileNet? I think it was MobileNet like V1 or V2 that was pre-trained on either ImageNet or Coco. Can't quite remember. Awesome. Thanks, Jen. What kind of loss function are you using? If you give me a minute, I'll have to switch over to expert mode. One of the Edge Impulse people can probably answer that. Okay, does it give me a number saved? It doesn't give me a GPU runtime number. Shoot. Okay, let's switch over to expert mode real fast. And it wasn't my optimizer. You're asking about loss. Somebody spots it, let me know over here. Sequential. Okay, so there's my optimizer. Yeah, I can't quite remember what the loss function here is here. If you spot it in expert mode, let me know. I thought it was not import Atom. Yeah, I can't quite see it. I know it's using the Atom optimizer. Okay, I hope that helps. That's a good one. I'll have to look that one up. Like, what's the loss function? It's basically whatever the default loss function is in Keras when you create neural networks. Yes, thank you. Categorical cross entropy. Alessandro spotted it. That's the one, because when you're not doing a binary classifier, you have to use categorical cross entropy. It's on here somewhere. Here it is, down at the bottom. Thank you, Alessandro. I was just looking in the wrong spot. I could have just done like a control F for loss, right? All right, so 3 o'clock. Any other final questions? I can stay a little bit. It's there. Yeah, just learning to read is a good one. So yeah, it was here. I was just looking at the wrong spot. So I will end it here. If anybody, like I said, if anybody has any final questions or questions after this, feel free to reach out to me on Twitter. And I went to the wrong slide. Burn through these. There we go. Here's the final one. If you're interested in this type of information, what I showed you in this course comes from 2 different lectures that we dive into data augmentation, looking at saliency and class activation maps. That's part of the course. There's this Coursera course. It's free for anybody with optional certificate, computer vision with embedded machine learning. There is a link to it. It is done by, I am the lecturer for the whole thing, but it is done by Edge Impulse, and we use Edge Impulse to train all of our models. And if you buy the hardware, you actually get to try it out on either, right now, OpenMV or Raspberry Pi is supported. I'm hoping for new microcontrollers in the future, as per Edge Impulse's announcement 2 days ago. So that would be fun for object detection. I want to thank everybody for joining me today. I think this concludes essentially Imagine, and I hope everybody had a fantastic time at the conference. Thank you all.